Welcome to the deep dive. Today we're diving into something pretty fundamental, something that really shapes how we see the world. It's the basics of statistics, specifically how we gather and present information. When we're talking about groups of people or things, we've got some really interesting resources here that break down these core ideas.
Yeah, think of it like equipping yourself with a new lens. We want to go beyond just understanding data at face value. We want you to be able to actually critically evaluate how it's collected and displayed so you can kind of see through the noise, see through potential misrepresentations, and really figure out if those numbers are actually reflecting reality or if there's some kind of spin being put on things.
Exactly. And we're not going to get bogged down with, super complex equations or anything like that. Our mission today is to make sure you have a really solid grip on those foundations. Like, how do we even define the groups we're interested in? How do we select a representative snapshot of that group? And then how do we organize and visualize that information in a way that's both clear and honest?
Right. And I think a good place to start is by understanding those basic building blocks, populations and samples.
Yeah, the whole shebang.
Exactly. So in statistics, when we talk about a population, we're talking about the entire group that we're interested in, like the whole kit and caboodle.
Our sources give this really clear example. It says, like, imagine a group of hotel owners in a city. They want to understand what people in the city think about casino gambling. In that case, the population would be every single person living in that city.
Exactly. Now, obviously, it would be a pretty massive undertaking to try to survey every single resident. It would be pretty impractical. So that's where the idea of a sample comes in.
A taste test.
Yeah, it's like a smaller group, a subset. We select it from that larger population.
Like, you wouldn't eat the whole dish, you'd just have a bite to get an idea.
Precisely. But here's the catch. That bite, that sample, needs to actually represent the whole dish. We need to be careful about something called a representative sample.
Okay, so representative sample, meaning its characteristics really mirror those of the entire population.
Exactly. If your bite of food is just one ingredient, well, that doesn't tell you about all the other flavors. It's trickier than it sounds, though. Even when we're trying to be really careful, there can be subtle biases that creep in. For example, think about phone surveys. You're automatically excluding people who don't have phones, right? And that might not be a big deal, but depending on what you're studying or who you're studying, that could be a pretty big bias.
And our sources have this great example of a sample that probably isn't very representative. Imagine one of those hotel owners in the city. He suggests just going to like 6 of the hottest nightclubs on a Saturday night and surveying people there to try and get a sense of like the city's overall opinion on casino gambling.
Right. That's a really interesting example of what we call selection bias. Because think about it. People who go to nightclubs might have really different lifestyles and opinions than, say, people who don't.
Like way different.
Right. Like they might be more open to things like gambling in the first place. And so their opinion wouldn't necessarily represent, families or older folks or people with different social habits. Basically, that sample from the nightclubs, it wouldn't really give you a fair picture of what everyone in the city thinks.
So you can't just pick any old group. You got to be smart about it.
Okay.
Okay, so we get populations, we get samples, and why it's so important to have a sample that really reflects the whole group. But how do we actually do that? How do we make sure our sample is representative?
That's a great question, and that's where the principle of random sampling comes in. It's about giving everyone in the population a fair chance of being included.
Okay, random sampling. It sounds simple enough, but is it really just like picking names out of a hat? I mean, how do you actually make sure it's truly random and unbiased?
Yeah, you're right. There's a bit more to it. So a random sample means every single person, every element in the population has an equal chance of getting picked. This helps to minimize bias because everyone has the same chance, and it increases the chances that your sample will actually represent the whole group. Now, in practice, it's not always as easy as just like picking names out of a hat. Sometimes researchers use something called stratified random sampling, which means they make sure to get a certain number of people from different subgroups within the population, like different age groups or ethnicities.
Okay, that makes sense. But how do we actually go about obtaining a random sample? What are the steps involved?
Our sources lay out a pretty clear method. First, you got to figure out exactly who's in your population, every single person. Then you give each person a number, a unique identifier. And then you use some random method, like a random number generator. Or maybe you write those numbers on slips of paper and pull them out of a hat to pick your sample.
Makes sense.
And whichever numbers you pick, those people become your random sample.
All right, so let's go back to our hotel owners who are trying to figure out what the city thinks about casino gambling. They had a few different ideas for getting a sample, right? Let's analyze those, keeping in mind what we just learned about random sampling. What if they randomly survey people who live in, like, those fancy oceanfront condominiums?
Okay, well, if we're thinking about random sampling, we have to ask, does picking people from just those oceanfront condos, does that really give everyone in the city an equal chance? Probably not, right?
Not really.
And plus, people living in those condos, they might have strong opinions about having a casino nearby, maybe because of property values or traffic, things like that.
Yeah, they'd be more directly affected.
Exactly. So their views might not be representative of people who live in other parts of the city who might not be as affected by a casino.
Makes sense. Okay, so that's not really random. What about surveying the first, say, 200 names in the city's phone book? That seems a bit more random, right? At least on the surface.
It seems that way, but think about who's in the phone book. It's only people with landlines, right? And who even uses a landline anymore?
True, lots of people only have cell phones.
Exactly. And you're also missing people who chose not to list their number. So using the phone book, you're excluding a whole bunch of people. Again, not really random.
Right, I didn't even think about that. So both of those methods, not really random. But there was another option, one that our sources highlighted as being more appropriate for a random sample.
Yeah, the idea is to randomly pick different neighborhoods in the city and then within those neighborhoods randomly survey people.
Okay, why is that better? Why does that get us closer to a truly random sample?
Because by starting with randomly picking neighborhoods, you're more likely to include different types of people from different areas of the city.
More diversity.
Exactly, like different income levels, different ethnicities, all that. And then by randomly picking people within those neighborhoods, you're making sure everyone has a chance to be included.
Okay, so it's like layers of randomness to really capture the diversity of the city.
Right. And that gets you closer to having a representative sample.
Got it.
Right.
So let's say we've done all that. We've managed to collect a pretty decent random sample. Now what? We're faced with a mountain of data. How do we even begin to make sense of it all?
That's a great question, and that's where descriptive statistics comes in.
Descriptive statistics.
Yeah, this is all about how we take those raw numbers and we organize them and we summarize them and we present them in a way that actually tells a story. And one of the most basic tools we use is called a frequency distribution.
Frequency distribution. So like how often things happen.
Exactly. A frequency distribution shows us how often each value or category shows up in our data. So instead of just a jumble of numbers, we get a clear picture of how our data is spread out. We can even go a step further and look at the proportion of data in each category. This is called relative frequency, and it's really useful when you want to compare different sets of data that might have different overall sizes.
Makes sense. Our sources actually give a great example here. They look at the age at which 35 boys experienced their maximum growth spurt in a year. They list out 35 different ages.
Yeah, just a long list of numbers.
And it's hard to see any pattern in that, right? Just looking at the raw data.
Exactly. That's where the frequency distribution comes in. It helps us see the underlying pattern.
So how does that work?
Well, you create a table.
Like a chart.
Yeah. In one column, you list all the different ages where those growth spurts happened. And then in the other column, you put the frequency, which means how many boys had their growth spurt at that age. So, for instance, the table might show that one boy had his biggest growth spurt at age 10 and two boys at age 11, and so on.
Right, it organizes the information.
Exactly. And then when we look at that frequency distribution, something pretty interesting jumps out. We can see that most of those boys, they hit their biggest growth spurt somewhere between the ages of 12 and 15.
Makes sense. Those are prime growth spurt years.
Right. And we can also see that the age with the highest frequency, the age where the most boys had their growth spurt, is 14.
Okay, so 14 is like peak growth spurt.
Exactly. And this pattern, this concentration around age 14, it's much easier to see when you look at the frequency distribution compared to just trying to scan through that original list of 35 numbers.
It helps to visualize the data.
Right. And we can see the overall trend, too. Like the number of boys hitting their peak growth increases up to age 14, and then it starts to go down after that. So the frequency distribution tells us a story about those growth spurts that we wouldn't be able to see as clearly just from the raw data.
Okay, that's super helpful. So frequency distributions are great for understanding the spread of individual data points. But what happens when we're dealing with a wide range of values? Like, wouldn't that frequency distribution table get super long and messy?
That's a good point. And that's where we use something called grouped frequency distributions. Instead of listing every single value, we group the data into classes or intervals.
Our sources use this example of test scores.
Right. So say we have a bunch of scores ranging from like 40 all the way up to 90.
A pretty wide range.
Yeah. And listing every single score in a frequency distribution table wouldn't be very helpful.
All right, too much information.
Exactly. So instead, we create these classes, these intervals, like maybe 40 to 49, then 50 to 59, then 60 to 69, and so on.
Okay, so grouping them together.
Right. And then we count how many scores fall within each class.
Okay.
And that becomes the frequency for that class. And our sources talk about things like lower and upper class limits and class width.
Right, so what's all that about?
Well, the lower limit is just the lowest number in the class, and the upper limit is the highest number.
Okay, so for the class of 40 to 49, the lower limit would be 40, and the upper limit would be 49.
Exactly. And the class width is just how big the class is. So in that example, the class width would be 10.
Gotcha.
So basically, a grouped frequency distribution gives us a more summarized view of the data. It helps us see the general patterns more easily.
Okay, I get it. So we've learned about organizing our data, but what about presenting it visually? Because let's be real, a table of numbers is not the most exciting thing to look at.
You're right, and that's where visual displays of data come in. They help us tell the story of our data in a way that's easier to understand and remember. Our sources talk about histograms, frequency polygons, and stem and leaf plots.
Okay, let's start with histograms. Are those just bar graphs?
They are like bar graphs, but there's one key difference. In a histogram, the bars usually touch each other.
Oh, go. Why is that?
It's because the bottom axis, the horizontal axis, usually represents things that are continuous, like age or time, or it shows the boundaries of those classes we talked about in grouped frequency distributions. And the height of each bar, that tells you the frequency of that value or class.
Okay, so they're good for showing how the data is spread out.
Exactly. And then we have frequency polygons, which are basically line graphs. You take the midpoint of each bar in a histogram, and you connect those midpoints with straight lines.
Like connecting the dots.
Yeah. And that gives you a nice visual representation of the data's shape. They're especially useful when you want to compare different sets of data on the same graph.
Okay, what about stem and leaf plots? That sounds pretty complicated.
It's actually a really neat way to organize and display data, especially smaller sets of data. So each data point is split into two parts, a stem and a leaf. Usually the stem is the first digit or digits of the number, and the leaf is the last digit.
Our sources use those test scores again as an example.
Right, so say you have a test score of like 82. The stem would be 8 and the leaf would be 2.
Okay.
Then you list all the stems vertically, and next each stem you put all the leaves that go with it. So you can see the whole distribution of the data, but you can also still see the individual values.
Wow, that's a really clever way to organize things. Okay, so we've learned how to collect, organize, and present data. But as we mentioned before, visuals can be powerful, and sometimes that power can be misused.
Exactly. While visuals can help us understand data, they can also be used to mislead us, to create a false impression.
Okay, so let's talk about those deceptions. Our sources give this striking example using data about the poverty rate. They show how the same data can be presented in two different graphs, but one makes it look like the poverty rate is skyrocketing, while the other makes it look like a slow, gradual increase. How do they do that? What's the trick?
The trick is in how they manipulate the scale of the vertical axis. So if they stretch the vertical axis, meaning they use smaller increments between the numbers, even a small increase in the poverty rate can look really steep. But if they compress the vertical axis by using bigger increments, that same increase can look tiny.
So it's the same data, but the way they present it visually can completely change our perception?
Exactly. It's like they're zooming in or zooming out on the data to tell different stories.
Okay, so what are some of the things we should watch out for so we don't get fooled by these visual tricks? Our sources provide a helpful list.
Yeah, let's go through some of them.
Okay, first up, lack of a clear title. Why is having a title so important when we're looking at a graph?
Well, the title tells you what the graph is actually about, what it's supposed to show. Without a title, you're left guessing.
Okay, so it gives us context.
Right. And without context, it's easy to be misled.
Next one, misleading vertical axis. We already talked about the scaling, but what else should we be looking for?
Make sure the numbers on the axis are aligned with the tick marks correctly.
Okay.
If the scale is messed up or there are no tick marks, it can be really hard to tell what the graph is actually showing. Also, watch out for graphs that don't start at 0 on the vertical axis.
Oh, yeah, that's a classic trick, isn't it?
It is. It makes small changes look huge.
Okay, how about excessive cosmetic effects?
Yeah.
Like 3D bar graphs or crazy colors and stuff.
Sometimes a little bit of visual flair can be nice, but if it's overdone, it can actually make the data harder to understand.
It's distracting.
Exactly. The point of a graph is to show the data clearly, not to be a work of art.
Makes sense. What about unequally spaced time intervals on the horizontal axis? I feel like that's something I see a lot.
Yeah, that's a sneaky one. So when you're looking at trends over time, the spacing between the years or months or whatever on the horizontal axis, it needs to be consistent. If it's not, it can create a false impression of how quickly things are changing.
Like if the graph jumps from 2000 to 2010, it might look like there was a sudden change, when really, we just don't see the data for those missing years in between.
Exactly.
Okay, how about bar sizes not being proportional? That seems pretty basic, but I guess it can be tricky.
Yeah, so obviously the height of a bar should match the value it represents. But sometimes they'll use images or icons instead of bars, and those images might not be scaled properly. Like one image might be twice as tall as another, but not actually twice the area, which can be misleading.
Oh, I see. Our eyes can be tricked by that.
They can. Okay, another really important thing to look for, the absence of a data source.
Why is that so crucial?
Because you need to know where the data came from. Was it from the entire population or just a sample? Who collected the data?
It matters if the data comes from, like, a candy company versus a health organization, right?
Exactly. You got to consider who's presenting the data and what their agenda might be. And lastly, our sources give this really interesting example about these misleading visuals of houses that are supposed to represent average dwelling size in different years.
Oh, yeah, that one was wild. So the houses show additions over time, but the additions aren't to scale. Like the front porch on one house might be way bigger than it should be compared to the rest of the house.
Right. And the shadows they added are all messed up too, so you can't even tell how big the houses really are supposed to be.
So sneaky. And then on top of that, the years on the horizontal axis aren't evenly spaced.
Right. It goes from 1980 to 1990 and then all the way to 2020.
So it makes it look like houses have been growing steadily when really the biggest growth happened between 1980 and 1990.
Exactly. The visuals create a completely different story than what the actual numbers show.
Crazy how easily they can manipulate things like that.
Yeah, it just goes to show how important it is to really pay attention to the details and to think critically about how the data is presented.
So wrapping things up, we've taken this deep dive into some really important statistical concepts. We talked about populations versus samples and how to get a representative sample using random sampling.
And we talked about frequency distributions, how to organize data in a way that reveals patterns, and how to visualize data using histograms, frequency polygons, and stem and leaf plots.
But as we've seen, visual displays can be deceiving.
Absolutely. So remember to watch out for those misleading tricks like manipulated axes, non-proportional scaling, and the lack of a data source.
By being aware of these things, you can become a much smarter consumer of information.
Exactly.
So next time you see a graph in a news article or an ad or on social media, think about what we've talked about today.
Ask yourself those critical questions. Where did this data come from? Is this visual accurate? Or is it trying to spin a narrative? And ultimately, think about who might benefit from presenting the data in a certain way.
It's all about being a more informed and discerning consumer of information.
Exactly. That's what this deep dive was all about.
Thanks for joining us on the Deep Dive.